help get y'all ready for it. So go ahead and take out a piece of paper so we can write on stuff.
Yeah.
You don't know. So that way you will be ready for stuff tomorrow or Friday. So I'll help you get started for it. Alright, so thinking back over it, what is the equation if you're going from Celsius to Fahrenheit? So you're finding Fahrenheit. So you put the temperature for Fahrenheit by itself. Alright, we'll just start with Chris and we'll just rotate back and forth. This is the dice game. Alright, so if you're finding Fahrenheit, what's the equation?
5/9 times T9.
What's
Right,
that?
slanted and halfway sideways.
Parentheses. Celsius. You're finding Fahrenheit
You're finding Fahrenheit.
plus 32.
Alright, one part of this is correct. Alright, Ethan, you have a chance to fix it.
So one part of it is
One
correct.
part is correct.
It's minus 32.
Alright, final answer?
I think so.
Nope, okay.
I
Right.
can't get that one.
So, if you're
The other one's
finding
easy.
Fahrenheit,
Point.
9/, nope, either one of you.
Oh, I
Nine
knew
over-
that.
Temperature Celsius plus 32. You did have that part right. Okay.
Parentheses, right?
So, no parentheses. Alright, so how to help you remember it? The students last year remembered it as F for Fahrenheit, but then also fat. So it's 9/5. So
Oh.
it's a larger number. So I'm thinking fat, so larger number over smaller, and then you add it.
Easy now, I
So
get it.
add it. So they just remembered it as Fahrenheit. Fat is larger over smaller, and then you're adding it. So temperature in Celsius is obviously the opposite. So Chris will be the opposite for this one.
5/9 parentheses TF minus 32.
So they just remembered it as the opposite. And like I
Now I
said,
get that.
that
Do
they
I get the
remember.
point?
Yeah, but they remembered it as this one has parentheses because parentheses and C's look kind of similar. So if that helps you to remember, okay.
Oh.
Yeah, so that helps you to remember.
That's
Okay,
easy now.
Find tricks to help you to remember how you remember it. So find something to help you to remember it. So I know sometimes it's hard. So that's what I was talking about, that the C's look kind of like parentheses. So if you remember that, you should be good to go from that
Roll
point.
dice.
Yeah, roll your dice.
That's like in literature, like with the authors and stuff, like Bennett, it was like by at the end, like the B at the end, like how Matt's things up, and so I can memorize it easier.
Yeah, typically the stupider it is, the easier it is to remember it. So if you need some crazy thing to help you to remember it, I don't care. Help you to
I didn't even
remember
think
it.
about that, though.
But yeah, that's what they did last year, and I was like, that's actually a pretty good trick. I'm gonna steal that. So
Fat
that, so
It's
fat.
stupid like Nazism.
9, like it's a big fat
Okay,
9.
okay. If that helps you to remember, whatever it is.
Bro,
for
this
it.
is really easy now.
Alright, so which temperature scale? Oh no, well that's the other equation one. Alright, if I'm finding the temperature of Celsius and I'm going from Kelvin, okay, how do I find it? Kelvin. Okay, temperature in Kelvin.
Celsius to Kelvin?
You're going from Kelvin to Celsius, so Celsius by itself.
Oh, so you're going to Kelvin to Celsius? Plus 273.15. That it?
Final answer? No.
Minus.
Yes.
Come on!
Alright. So we'll talk this one to help you figure out a trick to help you remember. Alright, so what is 0? I'm gonna drop my chalk. 0 for Celsius. Like what happens at 0 degrees Celsius?
That water freezes.
Water freezing. Alright, so what happens at 0 degree Kelvin? Or what's supposed to happen is, like what's special about 0 degree Kelvin? Every time I write it, it looks like okay, and I try to remember that it's 0 degrees Kelvin, or 0 Kelvin.
I don't know.
Alright, remember it's based on absolute 0 or the coldest possible temperature. So can
That's the coldest
this is
temperature.
the coldest temperature. So can I get anything less than this? No. Alright, but what's gonna happen at 273.15 Kelvin?
That's where, that's like the hottest. That's where, I don't know, I don't remember Kelvin that much now.
Alright, these two temperatures are equal. So water freezes at 0 degrees Celsius, and at 273.15 Kelvin, water still freezes. So if this is 0 for, for Celsius, what do I have, so, which one's a lower point? 0 degrees Kelvin or 0 degrees Celsius?
What you're saying? Oh,
Oh, like on a temperature scale, which one would physically be colder?
the Kelvin.
The Kelvin scale. So for this one, just remember that this one, there's a 273.15 difference between them. So that's why for this temperature, this one starts at 0. So you're already at, by the time you reach to 0 degrees Celsius, you're already at 273.15 degrees. That's why if you gotta go back to the opposite, you have to subtract it out because the starting point is so much higher than it. So that's what will come for this one.
So
You have to
the
subtract.
other one's about to ask, aren't you?
Which one?
The other one you're about to ask, aren't you? Or it's
No, it's just the opposite. So there's no
so
point asking
TK
to say
equals
it.
TC plus 32.
Yep. Plus, keep in mind, alright, now here's a real question for you now since you already rolled. Can you have a negative Kelvin temperature? No, so if you get your answer and if you realize you got a negative Kelvin answer, you have done something wrong, you should go back the opposite direction.
Oh, that'll help too.
Yeah, so you cannot go lower than the coldest possible temperature. So if you see negative Kelvin, nope, I done messed up. You should go back and figure out some other direction. Alright, roll.
Oh, I did. You did, wait, what?
That was your question. Can you have a negative Kelvin number?
Oh, yeah.
Roll. Alright, so that's the major math we've done so far. Alright, if I have a positive exponent, really large number, really small number. Oh, like in 3.15 times 10 to the positive 6.
Okay, what are you asking?
Is it a really large number or a really small number?
Large.
Large, roll. How do you know?
That's not positive, not negative.
Yep. Alright,
It's
what?
9 or 6.
Yeah, if it has a line underneath the little circle part, that's a 6. What if it's negative 6? Ethan, really small, really large number, really small number?
Really small.
Yep, so look at the exponent and tell you which direction you're going. Alright, did you have a question?
Go ahead. That's like
I know, like I said, there's not a lot of terms in this section, it's mainly math. Alright, so we got into figs yesterday. So if I were to have 305, how many sig figs? 3, how do you know?
Well,
Wait, how do you know?
because there's 3 numbers up there and there's a 0 between 3 and 5.
Good job. Alright, what if I were to have, this? How many sig figs?
4.
4, how do you know?
Because of the decimal. After it.
After the left, to the right of the non-zero digit. Alright, what if I have this? How many sig figs?
4.
Why?
There's a score after the decimal.
Ooh, but are they to the left of the first non-zero digit?
So there's
Wait, they're not to the left of the non-zero digit?
it's not a 0.
What? Okay, you're shaking your head, so that's how I'm trying to figure out what you're doing. Okay.
There's 1.
Okay, so there's one sig fig. Do these zeros count?
No.
Why?
Because they're not to the right of the decimal.
Good. Well, wait, right?
Right of the number.
Good job. I'm just making sure. Just making sure. Alright, let's see if I were to have, alright, now how many sig figs?
4.
Why?
Because after the 0 after the decimal.
This one?
No,
Okay.
after the 5.
Yeah.
That's after the decimal and after a number.
Good job. Alright, so it is 2. The right of the non-zero digits, and there is a decimal point. Roll. Alright. I think that's all the major rules that we've covered for it. Like I said, we've been doing mainly math for the last couple of days, so there's not a whole lot of terms.
Last year when we were doing that, or physical science, I think, sig figs, I didn't pay attention to that part, so I didn't know what it was. So when we went, that's why I wasn't getting them, because I didn't know what they were.
Yeah, that's the
That
goal
was
this
easy.
year. I'm making sure we're drilling it very intensely with them
It's easy.
and making sure that they get it this time around. Because yeah, if you don't get it then, now in biology you don't really use sig figs, so something where okay you might forget them, so it's normal to forget them, but you use them a ton in chemistry and then you use them again in physics. So that's what you got to know them now. All right. Okay, we didn't really have any other terms lately, so go ahead and turn over to page 15 and you check. Oh yeah, points. How many do you have? Let's see, 15 or more? You didn't have a whole lot of terms though.
I just got 15.
I had 17.
Alright, you win. Don't forget candy.
You can have my candy.
You may put your dice in your pocket, but do not history class later. Alright, turn over to page 15. Let's do application. No, I went through how to solve with addition and subtraction and multiplication yesterday with sig figs. So, do number 4 first, application number 4. That should take you maybe 3 minutes. Maybe. Because you're
Wait,
just
what?
saying, for application number 4, you're saying how many sig figs are each of the numbers. I want you to be really straightforward. Number 5 is going to be slightly harder. You're going to solve the calculations. Page 15, application 4, all of it. And then application number 5. Application number 5 is perform the following calculations using significant figures properly. So you can use your calculator. So we're not testing your testing your ability to solve math. I'm testing your ability to see, okay, can you apply sig figs once you've done your calculations? I believe I talked over this yesterday, but we didn't have any time to practice.
Is 4 and what?
4 and 5. So all of 4 really quick, and then number 5. Yeah, number 4 should take you maybe 2 minutes. Maybe. All you're doing is you're just saying how many sig figs there are. You've already finished all your calculations, remember that? You've already rounded for proper sig figs.
I'll be done in a minute.
Alright, let's go over number 4. I think we might have done part of this one in class yesterday. I don't remember for sure. Let's go over it really quick. Alright, how many sig figs, Chris, for letter A?
3,
Good job. How many for letter B, Ethan?
2,
Good job. How many for letter C, Chris? Alright, how many for letter D? Ethan.
5,
Good job. Alright, E, what do you got? Good job. And then last one, letter F, Ethan.
3,
Ooh, why? Alright, why does this one have 3?
because a 5 and then a 5 and then the 0 after the 5.
What about the 0?
Oh, there's a 5 right behind it though, right? So
Yeah, so it's sandwich. So do the ones in a sandwich
the
count?
4.
Yeah, this one's 4. That's okay, just be careful. Alright, let's go over the calculation part for it. Alright, what do you have for your answer to letter A, Chris?
301.941.
Good job. And what is, so for this one, I'm going to go ahead and just write out your full answer for it. 301.941.
Oh, I'm writing them after I do it, so I don't
That's-
have this.
It's okay. So what would you round this to if you're thinking about for proper sig figs of calculations?
301.
Why?
Because the 201, that's the lowest.
Good job. That's the least accurate. But then I'm going to 301.9.
So 302?
Yep. So for this one, it just becomes 3. Wow.
Oh, so we divide them. Okay.
Wait. You divide?
No, you round.
Yes, you
And
still round for it, but
Okay.
you're right that yes, you round to the least accurate spot. So look at the right after the least accurate spot. Do I round up or do I round down? Alright, so this is the answer for letter A. I think we might have started these yesterday. I think we ran out of time. Alright, letter B. Chris, what you got for that one?
404.6.
Yeah, so 404.6. Alright, so what did you round this one to?
405.
Good job. So it becomes 405. Alright, multiplication. Alright, what is the answer? Alright, so you have just your answer in your
I have
calculator?
it now.
Okay, what you got?
320,000. No, 3,205.5.
He's
Did
doing
you
number
divide?
D. He's doing number D.
Oh, so C?
Yeah, see.
Don't have that one.
Okay,
Just have
okay.
the,
We'll come back to you then.
0.65.
So, 0.65. Alright, so that's the answer in your
Yeah.
calculator. So how do you change it into proper sig figs?
Move the decimal over 1, so 6.5.
oh, right.
How many sig figs do you have? How many do you have now? Alright, how many are you supposed to have?
3.
3.
So it should be 0.65.
How many 6 figs do I have?
So 0.065. 0.00 or 6.05.
Let me think of. So you said what was the last one?
6.05.
But that's a different value than this one.
6.50.
There you go. So yeah, you can add on a 0 so it doesn't change the sign. It doesn't change the value. Doesn't change your answer. Adding on an extra 0 doesn't change the fact that it is still 0.65. You're just saying I have measured it out this far, so I know exactly how it is. But you're right. And you're right though. It should have 3 sig figs. So this is how you would change your answer to make sure it has proper sig figs for it. All right, last one then for you, Ethan. All right, what have you got for that one?
3,205.5.
Good job. Alright, so that's not a 3. 3,205.5. Alright, what does it round through to have proper sig figs?
0.3. How about 0.6?
0.6? Where are you getting 0.6?
The 5, right? I don't know.
Oh, you're rounding this part up here?
To the 5.
Oh, so you would say 3,000 like that.
I know, but isn't there only one sig fig?
There's supposed to be only one sig fig. You're right.
I don't know.
Alright, so how many sig figs are in this number?
1.
Alright, so I'm going to have to round to only have one sig fig. So how can I make this only have one sig
3.
fig?
It's just 3. That's right.
Very close. 3,000, because do these count right now as sig figs? Do the zeros count?
No.
Why?
Because they're after the 0, after the 3.
And
And
what
it's not
else?
saying much.
Yeah, and what's missing to say that it's not significant?
Dot.
Dot. Now what if you put a dot? How many sig figs do you have now? 4, now it's wrong. So that's probably the reason why. You gotta be careful. So for right now, you're just saying, I just rounded to one sig fig. This one has one sig fig, so I rounded this one to one sig fig. Now the second you put on that decimal point, wrong. So be very careful for your quizzes and tests. If I start asking for proper units, don't just think in proper sig figs. Don't just think, okay, decimal point. No, you have now made your answer wrong with number of sig figs. So be careful with that. Alright, anyone have any questions about that? Alright, that's pretty much it for the math for this section. Let's look over at the top of page 15 really quick. We'll talk through it and then we'll move on into chapter 2, moving away from the math section. Now keep in mind, I'm not going to go over math all the time. So as we're working with your equations, I'm going to start referencing sig figs and how to use sig figs over and over and over again. So just make sure that you're being careful and that you keep up on. Don't just think, okay, we're moving away from temperature scales, so I can forget it. No, you can't. So make sure that you are still focusing on them. Alright, so let's read on page 15. Alright, who wants to read first so it gives you a chance to speak as well? There's only 2 of you, so you're going to rotate. Who wants to go first? You're going today. Ethan looks happy. We'll let Ethan go ahead and get it over with.
Top 15.
Dr. Vinny.
Because much of modern chemical knowledge is taken mathematically, your study of chemistry requires fundamental algebra concepts such as manipulating equations. One of the mathematical skills most useful in chemistry is the ability to solve literal equations. Equations in which most or all quantities are represented by variables. Solving literal equations can help you understand relationships between quantities and will allow you to answer.
Is that any operation can be performed on one side of an equation as long as it is also performed on the other side. Consider the equation triangle E equals Q plus W. I don't know what that sign means.
It's delta.
Delta E read as delta E is a single variable. If we know the values of delta E and Q, then we'll have to find the value of W. We can solve for W by subtracting Q from both sides. The rearranged equation can be used to find W for any values of delta E and Q. In contrast, if assume delta E and Q before solving will require solving the equation separately for every set of values.
Basically, it's saying you're going to use algebra, is what it's saying. That if you have an equation, you should be able to move your variables around in order to solve for each part. You don't have to memorize a whole bunch of equations. Now, sometimes your book only gives you the basic equation from going from Celsius to Kelvin, because if you know the opposite, then you don't have to memorize a whole new equation all over again, and it's to help you save time. All right, Ethan, read the last paragraph section.
Performing the same operation on both sides also uses solve equations involving multiplication, division, however, and rings. For example, the density equation can be solved for volume, by multiplying both sides by V and dividing both sides by P. Similarly, the following equations can be solved for A by dividing both sides by K and taking the square root.
So basically it's just showing you how you solve it. Now your book walks you through on page 14 over how to solve problems. We've been doing that whenever I'm asking like what are you starting with, what conventional analysis, where are you going, how do you get there. Your book's just trying to tell you in words how to solve it. But we've already been doing that, so I'm going to skip over it. If you want to read it, you can. You're not going to be asked any quiz or test questions over that section though. It's just telling you this is how you solve it, but it'll make more sense as we practice. Alright, any questions about chapter 1? We'll move on. Chapter 2, the nature of matter. Alright, what is matter, Chris?
Matter is undefined as anything that occupies space and it has mass.
Good job. So make sure you mark the definition in your book. Matter is undefined as anything that occupies space and has mass. So your desk is made of matter. Basically, everything you can touch and feel and taste in the room is made up of matter. Now, some things like light is a form of energy. Heat is a form of energy. So not every single thing, but as a good something, you can pick it up, if you can bite it, not that you should go around biting anything, but if you can touch it and interact with it, it's probably a type of matter. Alright, your book points out that God created everything ex nihilo. Alright, anyone remember what that means? We talked about physical science and I believe biology a little bit? Out of nothing. So, God just decided, I want to make everything. He decided at one point, at the very, very, very beginning of time, I want to make basically everything. So he made everything out of nothing. Alright, Ethan just finished reading the last section, so we'll let you read the verse. So go ahead and read Hebrews 11:3.
Through faith we understand that the worlds were framed by the word of God, so that things which are seen were not made of things which do appear.
Alright, so just make a note though that not only is it an Old Testament concept in Genesis, the New Testament references as well. That's part of the reason why people that don't believe in biblical creation have a problem, because it's not just in Genesis, it's all throughout the Bible. It's part of the reason why if you choose to not believe in creation, you're going to have some other problems with other doctrines in the Bible, because it's not just referenced in Genesis. Other people reference it. Even Jesus references it. So you're going to have other issues if you choose to not believe it. Alright, so matter. Matter is often defined as anything that occupies space and has mass. Alright, so states of matter. Your book goes over the general states. We talked through this with homework a couple of days ago, but we got to go over it again. So, when dealing with a single substance, temperature is the most important factor to determine a state of matter. Your book gives you ice as a common example. Alright, if you have frozen water, what state of matter is that in? Solid, liquid, or gas? Ethan? Solid. It is pretty much frozen. It's not really moving anymore. Now, ice is unique because ice typically expands whenever water freezes. Ice actually, this is one reason why if you take a water bottle and stick it in the freezer, your water bottle may or may not survive, depending on how much water you had in it and the type of water bottle it is. Your water bottle might very well explode. So that's probably the reason as to how come you're not really supposed to stick in the fridge. Now again, depending on the type of water bottle and how much water you have in it, it does affect it. But if you take little cheap Walmart plastic ones and shove them in the fridge, typically they're not gonna make it. Yes, Ethan.
At work, when I was working at a cabin shop in the summer, I had a water bottle and I put it in the freezer, this was like this.
Okay.
And I had to fill it all the way top and it exploded.
Yeah, that's probably the reason why, because I use water when whenever it forms up those bonds and how it forms to make ice, it basically takes up more space than the liquid version, whenever they're all next to each other. So as you have their bonds come up and they expand out, they basically rupture whatever's around them. So again, that's the reason as to how come your parents and then your coworkers probably told you don't stick it in the freezer, because it'll freeze and rupture or break your water bottle. Alright, so just make note, your book points out first off that there are several different types of energy. Now, we measure your temperature by measuring loosely what your internal temperature is. Whenever I take your temperature in the morning, or Mrs. Keys or whoever it is takes your temperature in the morning, we aren't taking the thermometer and inserting it into your body to measure how much internal energy you have. We just take the laser and just scan you. So it's an indirect measurement for it, but it's a good idea to try to have a general idea over what your average internal temperature is. Alright, there are three different types of kinetic energy. So just make it up, kinetic energy is energy of motion. So if you have energy of motion, what's happening?
Moving.
It is moving. So I'm not going to hit you. But if I were to throw the chalk The chalk was moving, it had kinetic energy for it, and now I have broken chalk pieces on my ground, so it's probably not the best idea in the world. But that is the idea of kinetic energy. So, I'm not trying to hit anybody or hurt anybody with it, but that's an example of kinetic energy. Your book has the diagram at the top of the page, kind of showing you these are different versions or different types of kinetic movement, because you might be thinking, well, I don't have kinetic energy, I'm sitting still right now. Your atoms are even though you're sitting still, your atoms are still vibrating. Plus you have your blood circulating, plus you have electrical impulses. So even though you were being still in your chair, you were still having energy on the inside. Your body's still generating heat. So you don't have to know the different types of energy at the top of the page. Your book's just pointing them out to you, just so that way, you're aware of the different types of kinetic energy. I have moving animations to help you see them, which I know it feels in chemistry like this is really basic. It's okay. So the first one is translational motion. It's moving across the room, or it's moving. So translational, or it's moving somewhere. So like throwing chalk or throwing the ball. If you remember last year, the different types of games I would have with like the little bitty hacky sack. I don't know if I ever played that in biology. I did not, but because of Corona, I can't play this year at all. So you would be throwing the ball or the hacky sack around. Can't do that at all this year. Another one is rotational. If it's rotational energy, what's it doing, Chris?
Working.
Yay! Yeah, I know this feels really easy and really basic. It's just pointing it out to you for right now. So rotational energy. And the last one, this is the one that you're currently doing, even if you're not moving, vibrational energy. So if it's vibrational, Ethan, what's happening? It's vibrating, or it looks like it's spazzing. But yes, it's vibrating energy. Raise your hand. What?
Parkinson's is happening.
Be nice. They can't help that. But yes, it's the idea of they are vibrating in place. Now your atoms are doing this. Even the desk is vibrating very, 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 very smallly. But it's not enough to feel it like an earthquake. It's not doing that. It's a very slight vibration. And you're so large to where you don't even notice it. But the desk is vibrating, but it doesn't have enough energy to be able to have it vibrate apart and break apart at that point. So again, you might just point out there are these are three basic types of kinetic energy, but just note kinetic energy is the energy of motion. The temperature of matter is an indirect measurement of the particle's average kinetic energy. That's what comes. We take your temperature. It's the average. Figure out what's your average internal body temperature. Different points of your body have different temperatures depending on like the surface area of your skin. They can absorb heat. But on the inside of your body, your heart needs it to be a certain temperature all the time. That's what comes whenever you take your temperature, you're taking the average for it. Alright, there are three common states of matter. You probably already know this because you wrote these, I believe, in elementary. Alright, what is a state of matter?
State of matter. So are you asking what the three types are?
I can take all three other one, but that works.
Gas, solid, and
Did you say mass solid? Gas, solid.
liquid.
Liquid, good job. So your book has a picture of them on the next page, or you can see on this page, do mark what's solid. A solid is characterized by a definite shape and volume. So your desk is a solid. Now let's say I wanted to remake the desk. What would I have to do, Ethan?
Beat it to pieces.
Beat it to pieces, or you might heat it up to a very high temperature and weld on a different piece. Like if that bar on the side, occasionally, because students put their weight on this bar on the side, occasionally this breaks. Not all the time, but occasionally you'll have it where this one pops off on the side for it. Sometimes master covers do it. Now, Mr. Keys or someone, if they want to fix it, they can't just go stick and stick it back on. That's not how it works. Typically you have to get a welder's torch or something else really hot and reattach it and remelt it basically back together. You're giving your solid, you're giving your solid energy to have it reattach or re-go back together. So we know a solid has a definite shape and a definite volume. A typical solid does not just a typical solid does not just change form. Your desk should not just randomly fall apart on you or change its shape on you. Your desk should stay still. Alright, so if you want to go from a solid to a liquid though, what do I have to do? Chris? I want to go from a solid to a liquid.
I'm trying to think, sorry.
No, you're good.
You melt it?
Yes, I got confused on what direction I was going for a second. But yes, you melt it. So if I want to go from ice to liquid, how much do I have to, no, that's a little bit too far from it. If I want to go from a solid to a liquid, what do I have to do to my ice?
Melt it.
Wait, so how do I melt it? What do I do?
Take it outside.
What?
Take it outside.
Okay, and once it's outside, what's it doing?
Turn
Why?
water.
Why does just bringing it outside make it turn into water? It's not just like outside water. It's hot. It's hot. So you're giving it
Heat.
heat or energy is what I was looking for. So your book gives you the definitions for it. Now I know this feels like if we learned this in 6th grade. Yeah, I know, but your book is making sure that you know because you're gonna have to work in calculations in this later. So it's making sure that you are very aware of it. So I have a solid, like for example, for this one, I have ice. This is very badly drawn ice, but whatever. So ice, and I want to turn it into a liquid. I have to add heat into it, or I have to add more heat or a higher temperature to it. Now, if I keep adding heat to it, once it is a liquid, where will it go? What's the next state of matter? Ethan.
Gas.
Yes. All right. This is one reason why how many of you have made pasta or noodle. I didn't even finish my question. You were already raising your
Yeah,
hand.
because you know what you're about to say.
All right. How many of you have made pasta or noodles before? All right. So you know that you put your noodles in water on the stove. You boil them for so long. Now, whenever you're going to drain them, what do you have to watch out for, Chris? Now, whenever you're going to drain your noodles, what do you have to be careful with?
They don't go out.
Oh yeah, partly, but then should you just now your mom might have told you whenever you are dumping noodles into like the colander, do you dump it towards you or do you dump it away from you? Why? Yes, and the steam does not hit you because if you were to dump it this direction, what's in the way of all the steam rising? Your arms in particular, maybe your face if you're leaning over and staring at it. That's not fun. That's the kind of stuff your mom always tells you to pour it away. Which question? Okay, which statement? Raise your hand.
So maybe it'll make it cute.
Okay. But just keep in mind the reason why. The first time I made noodles, my mom thought she told me, and she either did and I forgot, or she just forgot to tell me. But I didn't know, so I poured it out, and I poured it towards the side, and my arm was still in the way. I got this nice crescent-shaped burn mark on my arm because all of the steam went up and struck me in the same spot on my arm. And I had a nice little crescent shape, and I had to go show her, look what happened to me. I was trying to help you, and I got burned. My mom basically told me I was being stupid because I shouldn't have done that in the first place. Yeah, but I mean, it goes away. It's not going to be forever there. But I mean, that's the reason why steam burns you. Now, think about it this way. Solid, liquid, and gas, which one has the most energy in it? Okay, Ethan?
Solid. Or gas. It's gas.
It is gas. This is one reason why. Now, you might think, well, I've been burned by metal before. Metal can burn me, yes. But metal has a higher melting point. It can absorb a lot of heat before it starts to melt. That's the reason why you can touch hot metal, like the seat belts in the summertime right now. You know the metal is hot. And that's the reason why if you touch it, that's why you get burned or it's irritating. Because the solid, it can't absorb a lot of heat. Now metal has such a high melting point though, it's not like water, to where water melts at 0 degrees Celsius or starts to melt at 0 degrees Celsius. About 0 to 4 degrees Celsius is whenever it starts to melt. So that's whenever water starts melting point. Metal has a much higher melting point. You have to heat it to a much higher temperature to have it start to turn into the liquid. That's what can make it get so hot before it starts to melt. Well, 3 states of matter, gas has the most amount of energy. That's why gas has a tendency to burn you if you're not careful, because it already has the most amount of heat in it. Now again, for a substance. So of the 3 states of matter for water, gas has the most energy. If you were to heat up my metal in my desk and heat it into the gas form, it would be extremely hot and it would probably burn you and hurt you and maybe catch you on fire. It would be very, very, very hot. Alright, so thinking about it with pizza as well for it, whenever you bite into a hot piece of pizza, typically what part of your mouth gets burned? Typically it's one particular section. Anyone think they know? Roof of your mouth, because what's sometimes your tongue, but typically it's the roof of your mouth. Alright, because what's on top of the pizza, typically? Cheese, but it's typically melted cheese at that point, or hot sauce. The sauce is a liquid, so between the crust and the sauce on the pizza, the sauce is typically the harder portion, and that's the reason why typically the roof of your mouth gets burned, or your tongue if you're just messing around with it, and that's the reason why. Alright, anyone have any questions about the 3 common states of matter? Alright, so just making a note though, I skipped over the transition from liquid to gas. What do you call that? Call that transition point between a liquid and a gas. Chris? If I need to go from a liquid to a gas, what do I have to heat it to? What point?
No. Yeah, it's 32 because the boiling point of water.
32 is the boiling point of water.
32 Fahrenheit?
32 Fahrenheit?
That's freezing.
That's like, I'm like, oh no, it is a point, it is a point, it's the wrong point.
126?
I think you're combining some different things. So, if you want to think of it in Celsius, you can. Okay?
Melting point.
If you're going from a liquid to a gas,
Melting point.
melting to go from a liquid to a gas.
Technically it is melting.
It's melting.
Because water is.
Aren't you thinking of boiling?
Yeah, that's what I'm
Boiling, that's all I needed. The boiling point, or 212 degrees Fahrenheit, or 100 degrees Celsius. Alright, so do make a note. Melting point is between a solid and a liquid. So melting point. Boiling point, liquid to a gas. So just make sure that you note the different points for it. You're going to use these in equations later on, so let's come your book, just making sure you are very, very, very aware of them. Alright, fourth state of matter that we don't have a whole lot on Earth, but what is the fourth state of matter, Ethan?
Wait, what?
Fourth state of matter.
Air?
Yes, not quite. Alright, do you know, Chris?
What?
Plasma.
I
Alright,
got
fourth
it.
state of matter. This one is super hot. Basically, you take the gas and you keep heating it up until basically the gas splits apart into like gas pieces or the ions. They're charged particles. This is what happens whenever, if you pull out a extension cord out of the socket slowly and you see that spark, it has basically supercharged the air right there into making it into, I'm taking the oxygen and making ozone. That's how come it smells kind of like static electricity. It smells kind of weird. That's technically ozone right then. So it's a type of oxygen that's broken apart into the ions. That's an example of plasma. We don't have this a lot on Earth, but since it occurs at such high temperatures, we think that this is what is in stars and the sun. So if it's in stars and sun, which state of matter, solid, liquid, gas, or plasma, is the most abundant in the universe then?
Yes. Plasma.
Plasma. Because we think it's in the stars, and if you were to add up all the stars in the universe, we think, okay, now again, on Earth, we don't really have it a lot. We have it in a couple of special situations, but that's about it. So speaking of fourth state of matter, that's whenever it's super hot, it breaks apart into ions or charged particles. If you're talking about the most abundant state of matter in the entire universe, plasma. But on Earth, we have just the solid, liquid, and gases. Alright, anyone have any questions about that? Okay.
So say you get like hot water and you put it on the stove to boil it, and then you have cold water on the other side, and then you're gonna boil it. Like, would it matter if it's hot or cold? It will boil faster.
So you're asking me, I have to think.
So you have cold water and you go to boil it, and you have hot water and you go boil it. Will it boil at the same time, or will one boil
These are cooking
before
pots.
the other?
I'm sorry, cooking pots. Alright, so this one has ice cubes in it, this one has regular water in it. So you're asking me at what temperature will they boil?
No, I'm asking which one will boil first. If it matters, if you put hot water on the stove and cold water, you're gonna make macaroni or whatever. You have water.
Ice water to make macaroni.
No, it's just
Okay,
you have
okay.
cold water. Like
Okay.
you have the sink on in cold water,
Okay.
or if you wait for it to go hot, like which one will boil first?
Okay.
Or does it matter?
Yep, it does actually. Alright, so at what temperature does water boil?
272, 90.
Well, it's 212 degrees Fahrenheit.
Oh,
Okay.
okay.
So 212 degrees Fahrenheit. Alright, so if this one is at, we'll say, I don't know, 52, because that's about room temperature degrees Fahrenheit. And this one, because it has ice in it, we're going to say it's around 46 degrees, so, Fahrenheit. Yep, that's not 46. Alright, which one is already closer to the 212?
52.
The 52. So this one, yes, will, if you keep everything else the exact same, you know, the exact same amount of water, just the temperature is different. This one, because it's closer, will heat up faster. Now they will both start to boil once they reach 212 degrees Fahrenheit. But since this one is cold, like in particular, if you have ice in it, no, I would remember that it's cold. But if you have a colder temperature, you have to go farther to reach that 212 degrees. So yeah, this one was technically more first.
Water, it doesn't matter if it's hot or cold or not. Okay.
I mean, it'll eventually boil, like, we're talking, like, maybe a minute difference depending how much water you got. So, I mean, ultimately, it doesn't matter. I don't know, like, I wouldn't go get, like, water out of, like, the freezer and then dump ice cubes in it and then start to boil, because that's going to take a little while. But, I mean, if you get it out of the fridge or out of the sink, that's such a small, minute difference. Like, they might be at that point, like, 52, 48 degrees difference. It's not going to be enough to, like, severely slow down your water. Okay, but yeah, but technically it would take it slightly longer. Alright, good questions though. Alright, anyone else with questions though about these states of matter? Alright, classification of matter. A substance is a form of matter with unique properties that make it different from every other substance. Alright, metal is different from water. How do you know? Chris?
Because substances have a set of shape.
Yeah, so you would know that metal is hard, water is not. Metal, you can, if you get a hammer, beat it. Water, you can't really do that to. Even ice, it might chip off in pieces. Ice is really, really, really cold. Metal might be more room temperature. There are several things that make it different. Your book points out in particular water and copper. So water is odorless, tasteless, colorless. I know some people say that water has a taste, specifically the ions or impurities on the inside of it. Copper is characterized by color and its metallic properties. Another common substance would be like the idea of salt and sugar. Alright, now if you look at salt and sugar and you know what you're looking for, you can typically tell them apart. But most people can't just tell. So what would be a major difference? How do you know if you have salt or sugar in your food, even?
What?
Okay, let's say that you have two containers and they both have the white grains on the inside and you know it's not cocaine. So how do you know, or how would you know which one's salt and which one's sugar before you add it to your food?
Try it out.
How? Taste it. You typically you typically pour some on your finger. Now, if you know what you're doing, you can look and say, like, okay, I can tell by looking. If you have enough practice, you can do that. But yeah, most times you just be that sugar, I'm not going to add that to my food, or, yep, that's salt, I'm going to add it to my food.
Be tasting pretty good, it's not cocaine.
Yeah, it's not. Your
Yeah,
house
I
should.
said that.
If it is, then you're dead.
I was like, wow, people get the salt and cocaine.
Alright,
cocaine.
no, that's what I know. I said it as a joke, but yeah. Now keep in mind that your house should not have cocaine at all.
Of course, but that's kind of common knowledge. Don't have cocaine in your house, kids.
Yeah, understand. Because you brought it up
If
as
you have
well.
cocaine in your house, you need to call 911 because your parents.
Alright, we gotta move on to that comment. Alright, so that is your butcher's point. That is one way to tell for the idea of sugar and salt. You can tell by taste. Now they look very similar, but if you put them on food, you know they're very, very, very different for it. Alright, atoms and elements. Now, the smallest particle you can get and have it still be a substance is an atom. Now, in some cases, you can get a substance be still the same type of thing and still have it be an atom. So this would be an element. Alright, yes.
Technically, electrons are smaller.
Then have it still be the same substance. That's why I said same substance. So, just make it out for it. So, eventually, if you were to cut smaller and smaller and smaller, you reach a point in which particles are no longer, they can be made smaller and still remain the same substance like copper or oxygen. These smallest particles are called atoms. In some cases, once you reach those smallest atoms point, we call them elements. We have 118 elements on the periodic table. Now, some of them occur naturally in the Earth's surface, and some of them you can only make in a laboratory setting. You want to start memorizing on page 19, the bold ones. So, like how you memorize the italicized prefixes, you want to start memorizing the bold ones, the name and the atomic symbol for it. Talk more about this tomorrow because I'm about to run out of time. But we're going to start probably drilling tomorrow. And about a week, maybe a week and a half, we're going to have the quiz over them. And you need to know all the bold ones. So we will start working them tomorrow. There's a couple of tricks to help you out with it. But some of them, as you look at it, you realize some of them don't mean that. Some of them you have to learn physical science already. So some of them you should already, so some of them you already be aware of. But some of them you should be like, okay, yeah, okay. If you've never memorized them before, then you need to start working on it. So about a week, maybe a week and a half, but it's coming up. Alright, did you have a question, Chris?
Yeah, I'm chilling. I already know this.
Alright,
I
good.
got Wesley.
Alright, so in some cases, whenever you have an atom though, you can have an atom, you can have them join up together to have a new type of substance. Once you have them chemically bonded together, they no longer act like they're individual atoms or elements that they originally were. Like for example, water is an example again. Anyone know what's the chemical compound of water made of? You don't have a water element, there is no water atom, okay?
Isn't it 2 hydrogen, 1 oxygen?
Good job. So it would be H2O, or it's bonded like this if you're drawing it out. So this is a water molecule. Now it's made up of oxygen and hydrogen. Now pure oxygen reacts very differently than a water molecule. Pure oxygen is flammable, it'll catch on fire. Hydrogen is also kind of explosive, but water isn't really explosive. It's because those chemicals are now hooked together, and how they're bonded makes them stable and makes them a lot more happy. Same idea with sodium, sodium chloride. Anyone know what sodium chloride, the common name is for it?
Sodium nitrate?
Nope, sodium chloride, like that's the chemical name for it.
Salt.
Salt, table salt. Now, sodium, if you get pure sodium and you drop it in water, it basically explodes. It reacts very quickly with it. That's the reason why you can't get a whole, wait. That's the reason why you can't get a chunk of pure sodium, or if you can, they tell you to be very careful with it. Alright, which question?
Like, it'll like explode quick?
Yeah.
And how big?
Depending on how big a chunk of sodium you start off with, a lot. If you take a small piece and drop it in water, basically it looks kind of like a little firecracker. Like it's not colorful, but it's reacting with energy.
Because I have like a big like block of pure salt.
Pure sodium or pure salt?
Pure salt.
Okay, salt, because it's bonded, it makes it stable. This is one reason why you can take sodium chloride and put it in your mouth and it won't explode, because sodium has reacted with the chloride at that point. It's stable. But if you were to take pure sodium, the sodium wants to react so bad, and we'll talk about the reasons why. It wants to react so bad that if you were to put it in your mouth, it would basically explode in your mouth and you go to the hospital. So that's part of the reason as to how it comes. Sodium chloride is safe. It doesn't do that because it's already chemically bonded. It acts entirely different than if you were to get sodium just by itself. Okay.
Can you buy pure sodium?
You can, but they start asking questions like, why do you need this? Are you with a school on like the websites? You can go to, you have it. Now sometimes, I don't know if they'll sell it to you since you are a minor. I don't know if they would even like consider it, because they want to, like for like the chemical websites, they want to know for me what my credentials are, what school am I with, and different things like that to make sure. Are you building bombs? Is basically what they're checking to make sure, or are you going to be safe with this? So that's what we're looking at. So you can buy it, but they start to get a little bit more picky, and it's not just like on Amazon. You want to buy some sodium? No. They want to make sure. Okay, are you actually using this properly? Okay.
Like, you know Belarus that exploded happened over there?
How recently?
Literally like 2 weeks ago.
Okay.
Like,
I heard about it, but I haven't looked into it at all.
So
Wait,
they
what?
think that there was terrorists and they're making a bomb.
Okay.
Oh,
It pretty much was like a nuke.
Is this fast? Is I have like 1 minute?
It went off like a nuke. I wonder if they were doing sodium, if it was sodium.
They could be. There's other ways to make bombs as well.
But it was so big, I don't know, like, you'd have to
that
have a
was-
massive piece of sodium to make pretty much the size of a nuke. Bomb the size of a nuke.
That was huge.
There's easier ways to make it at that point
That
than
was
using
huge.
sodium. Alright, we gotta keep going though. Alright, so just make a note though for it. Start studying off that table on page number 19. If you already know it, fantastic. Do make a note though that a molecule is just a group of 2 or more atoms that are linked together by chemical bonds. A compound specifically is 2 or more different atoms put together. So like a water molecule is made of 2 different atoms, so hydrogen and oxygen. Oxygen can exist bonded to itself as well. This is the oxygen in the air that you're breathing right now. That is not just one individual oxygen atom at a time. It's the oxygen, it likes to be bonded to something, so it'll actually bond to itself, and you'll have one molecule where you have the oxygen is bonded to itself. So just make a note, that's the difference between a molecule and a compound. A molecule is whenever you have the same atoms hooked together. Like if you were to have a block of pure gold, it's the gold atoms all hooked up together, or the molecules of oxygen hooked together. A compound specifically is 2 or more different atoms hooked up together. And I'm about out of time. Alright, you don't have any homework tonight because it's a revival meeting and want you to encourage you to go. Still be studying, no promises about tomorrow, so be studying, staying on top of it. And plus, you want to start studying the periodic table. Alright, thinking back over it, what is the energy of motion? Ethan?
Yeah.
Good job.
Most
Okay.
things